Okay, dear colleagues, let me announce the talk today. The talk is by Professor Bruce Westbury. He is retired from the University of Warwick. The title is on the exceptional series and the siblings. But before I want to give the word to Yassine Barhoumi to say a couple of words about the speaker. Okay.
Yes, hello everybody. So I know Bruce Westbury from the University of Warwick. He did his yes, I'm sorry. He did his studies in Cambridge, a PhD in Manchester. I think you defined it in 88.
I believe so.
Yeah. Went to MSRI and EHES, meanwhile. Then a postdoc at Warwick, the temporary lectureship in Nottingham, where he worked with John Barrett, and he's the co-creator of the concept of spherical category. And then went back to Warwick and worked on numerous topics. So I think on his most recent work, you got interested in cyclic sieving, but you will have a little overview of one of his latest work on the exceptional series and its siblings. So, ladies and gentlemen, Bruce Westbury.
Okay, thank you very much for inviting me to Sofia. It's the first time you're doing this.
We cannot see what behind you.
So, okay, but I thought the camera's supposed to be on. Right. Thank you for the invitation to Sofia. It is my first time in Sofia, and I hope you didn't party too hard last night. Happy Christmas. And are there any happy birthday to any Johns in the room? So this talk is more an introduction than presenting, the latest results. I did a lot of calculations in the 90s, and it never got published and written up. And so this is now what I'm trying to do. It's about log representation theory. So not everybody here is an expert in representation theory. If I don't explain something, feel free to ask. It's about highest weight representations of simple algebras, right? And it's more about a new way of organizing them, because normally you take a Cartan type and then you take a highest weight, and that's how you index all these representations. But this is a different way of kind of organizing them, which I will hope will make sense by the end of the talk. And I apologize, I didn't know, I wasn't given the right date for the talk when I wrote this. That's not today. So I'm going to start by talking about the exceptional series and try and explain what that means. I'm not expecting you to know what that means. And the title saying it's siblings is because Deline wrote a paper called On the Exceptional Series and Its Descendants. So it's a reference to that title. Okay, so
the point of driving. The focus was not on the slides as well.
Okay, good. So here's an outline of the contents. I haven't done the pause thing on the Beamer slide, so each slide that comes up, you're going to get the whole thing rather than me stepping through it and keeping half of it secret from you. So the introduction is what we're talking about now. Then the main topic is on the examples which are already in the literature, and then at the end I'll try and say where I'm heading with this. But the main point of the talk is to try and get the idea of, it's not known idea, this idea of series of representations. So the main idea of the talk is to try and get across what the idea of a series of representations looks like. It's not got a definition. There's just examples, and once you've seen the examples, you sort of know supposed to know. So there's a lot of data and formulae. So it's more sort of experimental mathematics, more kind of the way physicists would think than big abstract structures and theorems. Has anybody heard of the exceptional series before? Oh, okay, one. Is that it? Okay. So this is kind of where we start. So if you think of studying, things like finite groups, simple algebras, reductive algebraic groups, they're all what's called rigid. You can't put them in families. You can't deform them and introduce parameters. You can't. It doesn't work. So that's the wrong idea. But what you can do, and this is a fairly recent idea from that started the introduction of quantum groups, the Freudenthal and Jumbo quantum groups, was that you can deform categories. So you can take this category, which I would call the category of invariant tensors. So you're taking the objects are just the integers, positive integers, non-negative integers, and the Hom spaces or the vector spaces of intertwiners between tensor powers. And those categories you can deform as a category, so that there's more flexibility. And not only can you, that's what we want to do. And these categories have tensor products, symmetry, meaning you can flip the order of the tensor product. And if you're a physicist, you would just do these things without thinking about it. But if you're a mathematician, you make a sort of fuss about it. But these are just natural things, perfectly natural things to do. And you can put any of this sort of extra structure. You can throw in words into this category and add some extra words. But that's getting a bit technical, and I'll slide over that. Anybody want to ask anything on this slide? So the classical examples that have been around for a long time before all this work on quantum groups and things started are classical groups, and these are all the groups that are actually in Weil's classical book on classical. These are Weil's book, classical groups. These are the groups that he discusses. He doesn't discuss this idea of having a parameter, as far as I know. I don't think so. But the idea is that when you study any of these families of groups, this last one of the symmetric group. So I hope the notation is known. I mean, familiar with notation. But that's supposed to be an S for the symmetric group. And you don't study these examples by doing, you don't do, you don't study SLN by, doing your first course on SL2, and then the next semester you do SL3, and then when you're really advanced, you do SL4. It doesn't work like that. You just study the whole lot in one go and think of N just as a parameter. So, you can index representations by partitions. You can construct representations using semi-standard Tableau. You have, the branching rules are the Pierre formulae, and if you want to be more sophisticated, the Littlewood Richardson rules. And none of these things have any favorite N. None of these refer to any N at a time. They just work for N uniformly. And when you come to dimensions, then obviously the dimension does depend on N, but there's just the famous hook length formula, which produces a polynomial in N for the dimension. And the same thing for the other classical Lie groups, but it's just a formula just a little bit more complicated, the same idea, and the symmetric groups. And this is all fairly old representation theory. Weil's book was written in the 40s, I believe. So this kind of work sort of really was sort of really understood and worked out in the 40s. But the more recent point of view is this category idea. So instead of all these formulae become explained by by setting up category override properties where n is a formal parameter in the category, and then all these other formulae then follow from that structure. So you're abstracting, when you set up one of the categories, you're abstracting the properties of the categories of representation. You're taking the category of finite dimensional representations of one of these examples, and then you're abstracting the properties of the category, and then you're studying categories with those formal properties. And the Brouwer category is, the earliest example really, and that was Brouwer's paper was published in the Annals of Mathematics in 1937. So that he was ahead of his time in that sense. The partition category is more recent. That's Paul Martin and Vaughan Jones in the, I'm not sure, late 80s, early 90s. And all of these groups have quantum versions. So when the theory of quantum groups is introduced, these all have quantum analogues, and all this structure, the branching rules, Pierre rules, and all that stuff stays the same, but the dimension formula become Q analogues, the dimension formula. But this leaves out the exceptional simple algebras. So what I want to do is include. I've become interested in the exceptional simple algebras. All this classical groups is pretty much worked out. So the exceptional, if we're talking about the exceptionally algebras, we're talking about the exception segments. So when people talk about the exceptionally algebras, they would normally mean these last four and G2. They wouldn't normally include D4 or any of these other ones. They're normally people, you open a textbook and look up the definition, or go on Wikipedia and look up the definition of an exceptionally algebra. They would tell you it's these five: G2, F4, E6, E7, and E8. And part of what I'm doing is listing them as a series, because it's not, if you just look it up on a speed, you just get a set. I mean, it's just this list or set. Whereas what I'm doing is saying that there's a projective line, and each of these, each of the exceptionally algebras. Oh, each exceptionally algebras is attached to a point on the projective line. So there's a coordinate. So it's now more than just a list. It's now, each point has a point in this projective line.
So it's a family.
Well, we don't know what happens in between at this point. I mean, that's part of the point of the series, is to make this parameter continuous. At the moment, this M just takes on this finite set of values.
But what about OSP? This is a super algebra.
Yeah.
And the others are algebras. So why you include the super algebra?
Because it fits in. And I mean, I could put in a 6 and have, there's a more controversial one that's not really understood, but I've written a paper on it where you fit in a 6, and these come in pairs. I haven't said this, these come in pairs. So this D40 is a midpoint, and there's a reflection symmetry, and you can put the trivial representation on the end, the trivial group on the end here, and fit. There's just a lot of numerology. There isn't, these are the algebras that fit, and it's really based on numerology, not on any sort of great theory as about it. And the when you take this symmetry, you get dual reductive pairs in E8. So when you take the trivial group in E8, that's a dual reductive pair in E8. A rather trivial one. But A1 and E7 are a dual reductive pair in E8. A2 and E6 are a dual reductive pair in E8. G2 and F4 are a dual reductive pair in E8. and D4 is a dual reductive pair in E8. And so this extra pair of points where you have this group that I haven't put in, and this super Lie algebra, what I'm if you take what I said literally, you would say that what I'm saying is this super Lie algebra and this non-reductive Lie algebra form a dual reductive pair in E8, which obviously doesn't make sense, but that's why I've left it out, because you know, the numerology makes sense, but when I say it like that, it doesn't. And one of the ways of characterizing this list, why you call these simple, is that there's no primitive quartic Casimir. So there's always the quartic Casimir. Every simple Lie algebra has a quadratic Casimir. So that's the one everybody is used to. And you can square that and get a quartic Casimir. A Casimir just means an element in the center of the enveloping algebra. And you can square it and get a degree 4 Casimir. But that's not what we mean. You want a primitive one, a different one from that. And these don't have it. And if you look up the, you know, you can find things, Wikipedia or wherever, you know, in textbooks that will list the exponents of each of these Lie algebras or the Weil groups. You know, they're part of the structure of this. And if you look for the ones where 4 is missing, then you'll get this list, except D4, where 4 appears twice. So I don't know why D4 is, you know, so exceptional in that case. But apart from D4, when I don't know, you know, I don't have a Casimir story for the super Lie algebra or for the missing one. But basically it's if you look at the list of exponents and you don't see 4, then you can do the list. But if you're not seeing dual reductive pairs and all that, all you're supposed to get away from this is that it's not just a list, it's points in this projective line, and each of those points has a simple Lie algebra attached to it. So there's more structure, it's got more structure. And then we want this M. The idea is that this M should play the role of the N, and for the classical Lie groups we had N, which started out as just 1, 2, 3, 4, but then became a continuous formal parameter. So, you know, we would like this M to be, we want to think of this M as a formal parameter, and so sort of interpolate between these. We're only partially successful. I mean, that's the sort of idea. It probably doesn't actually work out. But it's not. So this is the more normal approach, the exceptional series, different approach, and this is much more what the talk will be about, is that when you take the adjoint representation and take its tensor square, you get this uniform structure. So when you take the exterior square, so this notation L bracket means the highest weight. So the thing inside the bracket is a highest weight, and then these are highest weight representations. And I'm taking the 0 is the 0 weight, which is the highest weight, dominant weight, and L of 0 is the trivial representation. And I'm using notation theta for the highest root, which is the highest weight of the adjoint representation. So L of theta is the adjoint representation, here's the trivial representation, and then you've got these other ones. So you take the adjoint representation and you look at its exterior square, and because of the Lie bracket, you know that you will get the adjoint representation back. So the Lie bracket is a homomorphism from the exterior square to the adjoint representation. So that's why that appears there. And the killing form is a symmetric invariant form on the Lie algebra on the adjoint representation. So that's why the trivial representation appears there. And then the question is, what's left after you've taken account those two? What else is left? And a fact which I don't think, I mean, I don't know if experts knew about it, but I don't think it was, written about in the literature. If it was that the complement of the adjoint representation is irreducible. So I'm just presenting this as you just check on a case-by-case basis. So, it's understood how to do these decompositions. And it's just a fact that the complement here is always irreducible for a simple Lie algebra. And the symmetric square will always contain highest weight 2 theta, because you just take the highest weight here and tensor V and take V tensor V, and that will be a highest weight in the symmetric square with weight 2 theta. So you're going to expect that. And so the point is that when you take that and now take the complement, the last one, that's irreducible. So this is what you observe for any of the algebras on the exceptional series. But these are just very short lists. So the only ones you don't, the extra pieces here and here are irreducible. A priori, they could have had more decomposed into more features. But for the exceptional series, that's what you get. So this sort of thing happens for the classical groups as well. So I mean, this is the sort of starting point to have this already. So for SLN, the fundamental representation, the symmetric square and the exterior square are both irreducible. So you see this is just slightly more sophisticated. I can't see who's talking. Okay. Is somebody saying something? Okay, we have to press on. So one of the things that makes this a series, where the parameter plays a role, is that you look at the quadratic Casimir, and the formula is this inner product where rho is half the sum of the positive roots. So this is the sum of the positive roots, and lambda is the height and weight of the representation. Then the Casimir takes this value. This is a classical standard formula in when you study simple algebras. And the values of the adjoint representation are in this series are given by these very simple linear functions. So this is the first time when you really see the parameter m playing something. So you can just substitute the m value for each of your simple algebras on the exceptional series into these formulas you don't need. They're behaving in this very uniform, simple way. Oh, okay. So I moved on to that was the end of my introduction to the exceptional series. I haven't given you the dimension formula yet. There will be some dimension formula appear a bit later on. So the next slide is on the Vogel plane, which is same idea but getting a little bit more complicated. Okay. So Vogel is Pierre Vogel. I always get called out on the way I pronounce his name. He's actually from Alsace, or his family's from Alsace. So it's a German word. I don't speak German. I'm sure plenty of people here will speak better German than me, but it means bird. It's a German for bird.
It's Vogel. That means bird.
Right, that's the German word. Yeah. That's the German pronunciation. He's from Alsace, which is now part of France. hasn't always been part of France. It's been in Germany, it's been in France. I've got a history that people in Bulgaria will understand better than somebody from England. Back and forth, borders moving back and forth. It's part of your history, it's not part of my history. But that's what they have in Alsace, and so he has a German family name, but he pronounces it in the French pronunciation. So he pronounces it Vogel. So if you speak German, you might call me out and say, what is he doing? Why doesn't he pronounce it the correct way? But no, this is his family name. It's a German word, but he's French, and so it has a French pronunciation.
Speak both French and German.
So here you just take any simple algebras. So before we just had a short list of simple algebras. Here now it's any simple algebra. And the difference is, so I use slightly different notation here, but so L is the adjoint representation. The exterior square works the same as before. You get the Lie bracket gives you the adjoint representation as a composition factor, and the complement of the adjoint representation in the exterior square is indecomposable. And the symmetric square, you have you again have the trivial representation.
But you have 3 pieces and you have 2.
That's right. That's right. That's right. That's the point. So you still have the trivial representation because of the killing form, but now I have 3, and last time I had 2. And I think Vogel was the first person to say this. Again, I mean, anybody since might have said this and might have noticed this. I don't know if they did. I'm not, I can't say that they didn't, but I'm not aware of anything in the literature that points this out. And this really surprised people when Vogel wrote his paper. And he wrote his paper in the 90s, but I don't know anybody who can explain it to me, and I can't explain it to you. He was interested in Vasiliev invariants, so it was after Barnatan had written his paper on Vasiliev invariants. And I'm speculating here, but I think there was a student who was interested in Vasiliev invariants working for somebody else as supervisor. It wasn't Pierre Vogel's student, and he was, he liked coding. He liked computers and coding, and it seems that he did a lot of computer calculations on Vasiliev invariants, and then left mathematics, and somehow Pierre Vogel's interpretation of his.
What's the name of the student?
Can I get back to you? He's got 3 papers on the archive. I can check it. Sorry, yeah. And so Vogel's papers are kind of read like, if you kept a journal by your bed and every time you woke up at 3 o'clock in the morning you started writing. That's what they read like. And I've never actually, they're fascinating, but the connection, the original calculations, the connection with the Vasiliev invariants I've never seen or met anybody who could explain it to me.
And you talk personally to Vogel?
Yeah, he came to visit at Warwick, and he got on the wrong plane. So I met him in Warwick, he came and I met him. I said, "Oh, how was your flight?" And he looked a bit embarrassed. And I said, "Oh, I pressed him." And the story came out that he'd actually got on a plane to Edinburgh. He bought a ticket to Birmingham, but when he got to the airport, he'd actually got onto a plane to Edinburgh. And it wasn't until he got off the plane in Edinburgh and said, "Where's the taxi to the university?" and got funny looks, that he realized he was in the wrong city. He then had to get a train from Edinburgh down to Birmingham, which is quite a train ride. I mean, it's not an overnight ride, but I mean, it's several hours, 6 hours or something. So nobody believes this story because everybody says it's impossible to get on the wrong aeroplane because we all taken flights and we all have our boarding passes checked at least 3 times before we get on the flight. So I can't explain that. But he wouldn't have made it up because he was too embarrassed to tell me. And why would he wouldn't make up a story like that. So I'm sure it's true, and can't tell you how it happened. But so that's sorry. I hope he's not listening. But this was very interesting work. It's been very influential. A lot of people have got fascinated. A lot of sort of papers have tried to follow up on it, but I haven't been able to understand the original papers, and they were only published recently, in the 20s, and they're really strange reading. And I think there was a disconnect because I think Vogel's background was in algebraic topology and algebraic K-theory, got was in Ciliac invariance. So he's very much a mathematician. And I think this other young guy was a sort of coder of computer thing. And although they were they were interested in what each other was doing, my feeling reading between the lines is that there wasn't good sort of communication. They didn't have the same background to enable them to really understand each other properly. They could have understood each other to sort of write things down and do calculations, but not to explain them. Anybody who wants to prove me wrong, please do so. So this is the same sort of structure as before. So all we've changed is we've added an extra representation to so you only need these 6 representations. So these, again, the sort of bizarre fact, but true. I don't, if you set out to prove this, if you know a proof where you can just prove that for any simple algebra this works, that isn't just a case-by-case check, I would be interested. Because Vogel didn't start with this. This came out of the calculations. It was, and that's what everybody else who's written papers just takes this as a fact that they've checked on a case basis. Whereas Vogel didn't. It came out of calculations on Ciliac invariance. And again, the Casimirs, we had simple formula for the Casimirs. So T is just the sum of these parameters, alpha, beta, gamma. So really, there's only 3 parameters, and then I can show you why this is 2t and this is t, why this should be twice that one. That makes sense. And then these have this simple formula, and this t is actually the Joule-Coxeter number. So that's not a new number. And the dimension of the adjoint representation is given by this formula. So it's homogeneous rational function of degree 0 in the 3 homogeneous parameters. So you should think of alpha, beta, gamma as homogeneous parameters on a complex on a projective plane. So before we had M, which wasn't a projected line, it was an affine line. But really these are but other people use different M's, and they all are different projected coordinates. So really the acceptance series is a projective line. And here we have this more explicit. We have three parameters, but they're homogeneous, and so this is really coordinates on a projective line. And I would say over the rationals, projective line over the rationals, but if you wanted to do it over complex numbers, I wouldn't argue with you. So that's the same, this Vogel plane, where it's a bit more complicated, this came first. And the exceptional series is actually a line in this plane. And that's what people picked up on. So people found Vogel's paper, had these strange facts that they weren't aware of. They got interested in it and saying, well, what's going on here? And then when they saw the acceptance series as a line, so well, let's start by studying this line. And that, Deline and Cohen and Deman wrote computer code and started doing all these calculations to explore this idea. but for the exceptional series, because that was a simple case to start doing calculations for. And there's a lot more known about the exceptional series than this whole plane, but this is what actually started the whole ball rolling. A technical point just came on the last slide is that you actually take the Lie algebra as a representation of the automorphism group. The point is that group, that as an algebraic group, doesn't need to be connected. The group of components is the group of diagram automorphisms of the thinking diagram. Because if you take D4, for example, you'll see loads more. If you just type the D4 into your computer algebra system and print these things out, you'll see much bigger lists.
And this should work for deformation, quantum?
Yes,
Quantum?
yeah.
Always.
Yeah, but people, yeah, so this all works for this. And then Ruben had,
But can you deform the other series, the exceptional one?
Well,
the quantum version of it.
well, there isn't, the exception series isn't really constructed in the way that I would want.
Anyway, do you think how to deform it?
Yes,
Yes.
Yeah.
I think it can be done.
yes. Yeah, I mean, that's part of this talk, that there will be this quantum versions for this, but what I'm trying to explain is I haven't got a definition of a series, I've got examples, so I'm trying to give an impression of what a series looks like. You can tell me to what extent I'm succeeding. So here's a picture. So I'm collaborating with Paul Zin Justin. So again, he's French. I've asked him about how to pronounce his name. He's in Melbourne at the moment, and he has. So he regards himself, he's just applying for Australian citizenship. So he's giving himself the anglicised pronunciation of his name. But I think the Justin, he would pronounce in a French style, but Paul has a French pronunciation. My French, I don't think I'd quite say it. Paul. It's more or less Paul, but because it's the French do say it in a way that makes it sound different. But my French accent isn't quite good enough. Maybe yours is. Anyway, yeah, and the Zin, the Zin, I think is just Zin. Regardless, I think that's not French, so I did, so anyway, it's one of these. So he's happy for me to call him Paul, Zin Justin. And he drew this picture for me because what I had on the last slide, these parameters is a symmetry. So alpha beta is a symmetry. So I'm not distinguishing, these are just three representations. So they don't come in any order. And, you can see that in these formulae, that this formula is symmetric in the three parameters. So when you draw the plane, you should actually draw it. If you follow that idea, you should actually draw it with the symmetry. So that's what he's done. So he took the point at infinity in the middle, because I drew pictures where I didn't do that and had these lines. I had to shrink his picture to get it on the slide, and then the labels will look horrible. So I removed most of the labels because I haven't labeled the exceptional series. So I think each sort of line is supposed to be a different color. So this yellow line, if we look at this yellow line, we see, so this looks like the orthogonal groups on this line. So I think this yellow line is the orthogonal groups, but there's the sixfold symmetry. What's this red line? I suspect this red line, the red is, looking at it, my guess is that's the exception series, because not many of them are labeled, but there's a few, A1, A2 are on the exception line. So I think that's the exception line. What's this one? D. So the A series will be here somewhere. A1, A2, A3. So that would be the SLN line. And there's a line where everything on the line is A1, just SL2. The whole line just SL2. I don't know. You can go a bit crazy drawing these lines. So should it be have this six-fold symmetry? Well, if you just look at the formula alpha beta gamma, yes. But then you could say, well, one of those representations is distinguished because one of the alpha beta gammas, it will be highest weight twice the highest weight of the adjunct representation. So if you can break the symmetry by saying, you know, alpha has to, or gamma, you probably pick gamma should be 2 theta, or the highest weight of y gamma should be twice the highest root. And if you said that, then you would break the symmetry. So then we wouldn't have such a mess on the screen. Or you know, so you can play around with what you actually want to put on this picture and how you want to draw it. Whether you anyway, find that some people like, you know, I don't know what we want to see in the picture. Okay, so that's the kind of history. So now we're going to sort of move on to what another sort of direction that people took the exception series. And this is the Freudenthal magic square. So he's German, that's supposed to be German pronunciation, so you can pick me up on my German if you like.
You don't speak Dutch?
He's Dutch. Okay. Yes, I went to Holland, yes, I know that. Yes, he's Dutch. Okay. Yep. He's Dutch. So anyway, so if you don't like that pronunciation, you can tell me and you'll be right. So this was an idea that goes back to the it was sort of developed in the 50s by Freudenthal, Tietz, and people like that in the 50s. And this was an attempt to understand the exceptional groups, not just as, you know, in the Cartan killing classification, you've just got the Dinkin diagrams of the algebras you'd expect, and then killing just found these 5 more. And it's just a list of 5. There's no reason where they come from. They just, you know, he has a classification and they appear. So, this was an attempt to kind of make them appear natural, like the other classical series that form a family, form a series. And the idea is you can construct them from the composition algebra, so the real numbers, the complex numbers, the quaternions, the octonions. And the reason you say that, you know, there's only this list is because this list stops here. You can't carry on past the octonions. So this list stops. So that's supposed to be the reason why there's only this finite list of exceptional, the algebras. And then what this magic square is a construction. It's a black box. When I gave this talk in Varna in the summer, I was asked to, or in Yerevan, I was asked to sort of explain this, you know, but it's a construction in terms of these composition algebras. And you put in a pair of composition algebras, and the output is a well, simple Lie algebra. And as well, yeah. So this is what you get. And in the 50s, what people were surprised because this had a symmetry. So if you take the 2 composition algebras in the opposite order, you get the same Lie algebra. But the construction, the Freudenthal Tietz construction, the original construction for this, they treated the two composition algebras very differently. It wasn't a symmetric construction, but the output was symmetric. So that was magic. That came as a surprise, and that was magic. There are now at least 3 constructions of this magic square. One of them is a triality construction in terms of D4, and that does treat them symmetrically. So if you took that as your definition, you wouldn't be surprised by the symmetry. So the numbers, if you